Okay, this is part 2 of the NEAP Physics 2024 Unit 3-4 VCE trial examination. We're getting into the written answer stuff. Okay, let's have a look at question 21. This is a very common question. This gets asked quite a lot. Analyzing connected bodies. All right, let's get into this. Question says a 2 kilogram block is on a table and connected to a hanging 0.5 kilogram block via a string and a pulley, as shown in the figure. The system of blocks is released and it moves. Ignore friction between the table surface and the 2 kilo block. All right, part A, show that the magnitude of the acceleration of the 2 kilo block is 1.96 meters per second squared. All right, one thing that a lot of people miss here, I don't think you've missed, I think I'm preaching to the converted here, but this is it. No matter how many forces there are on something, there can only be one acceleration. Right? You can be forced in different directions, but you can't move simultaneously in different directions. So there's only ever one acceleration. All right. So if we're trying to find the acceleration of the 2 kilogram block here, if the 2 kilogram block is accelerating, that will be accelerating as well. They're called connected bodies for a reason. This whole thing is going to accelerate. So you need to use F equals ma, but the F and the M and the A are of the whole system, right? So the M is going to be 2.5, excuse me. And the G is going to be 9.8. The force, by the way, is 0.5 by 9.8, right? It's mg. That is the only thing that's making this move. So there's only one force on the whole thing. There's no friction. The only force is the mass on this thing, the weight on this thing pulling it down, and it pulls everything down. So the F is 4.9 mg, right? 4.9. M is 2.5. Put those into the formula, find out what A is, and it equals 1.96. So part B, determine the tension in the string. And again, this is one that we've done a lot, but we haven't done it for a while. You consider one of the masses, all right? You either do this or you do that. It doesn't matter which one, but don't do both. There's no point, right? So you consider the 2 kilogram mass. I'm going to consider this one, and you do F equals ma again, but it's the force on that mass. It's the mass of that one, and it's the acceleration of that one. The acceleration of that one is 1.96, of course, because the whole thing accelerates together. The mass of that one only is 2, so the tension is 3.92 newtons. That is the only force on it. The only force that's on that is the tension in the string pulling it down. There is no friction. There is no air resistance that we're taking into account. If you did it for this 50 kilogram mass, there are 2 forces on this one. There's weight pulling it down, mg, which we did before, and there's tension pulling it up. That's the tension in both cases. Right? Tension goes towards the middle of a string or a cable, and it goes from both ends. That's why it's cancelled out when you consider the whole system. We didn't have to go plus tension minus tension here. So if you're just considering that, right, you're still doing F equals ma. Right? There's one A and there's one M. Right? So that's the ma. But in this case, the forces are mg minus t. Right? There's a force pulling it down, there's a force pulling it up, and this one's winning because it's accelerating down. Right? So it's mg minus tension equals ma. That's the formula. That's the sort of expression for F. And then you solve that for the tension and you still get the same answer, whichever way you go. Okay? So pick the thing that's got fewer forces on it and you'll do less calculating and you'll have less chance of making a mistake. Question 2, I really think it's worth having a look at NEAP's worked answer on this one. You need to understand that the answer to the question is the area under the graph. Okay, it says a rocket of that mass is going to launch from the surface of the Earth into an orbit of that altitude above the surface of the Earth. Figure 2's got a graph of the gravitational field strength versus the altitude of the rocket. Okay, gravitational field strength is mg. Altitude is h. That is the formula for gravitational potential energy. So this is a sort of a conservation of energy question, right? The area under the graph is going to be the gain in that energy between any 2 given altitudes, right? So that's what we're going to use to figure this out, because it says determine the minimum energy required for the rocket to reach an altitude of that far above the surface of the Earth. Now, 7.5 is about there. You've got to, you're in year 12, you've got to do this fairly accurately. I know it's a small graph. However, they're going to get you to pick it right there, 7.5, and find out the area there. Okay, that's what you have to figure out. Excuse me. So learn the area of a trapezium. That'll just make things a little bit faster for you. It's nice to know. Stick it on your cheat sheet, right? Go and look it up. You'll Google it in 10 seconds. And basically calculate that area. You need to figure out, you can either just do that, right? Or you can calculate the area of one of these squares and then count how many squares. I think it's easier to just figure out the area of a trapezium, right? But have a look at how they've done it. Now, part B is over the page. I'm just going to turn this for us. All right. Once the rocket has reached a stable circular orbit at an altitude of that, what would the period of the orbit be? Show you working. Okay, this, whenever you've got a radius and a period of something that's going around something else, you're going to use Kepler's third law. This is the only thing that you've got at your disposal. All right, so they're the keys. Right. If there's an orbit with an altitude and you're asked for the period, or the other way around, you have to use this. All right. Excuse me. And Kepler's third law, the understanding of Kepler's third law goes like this. I mean, that's just the formula. That's what you're actually going to use. But the point of it all is that is a constant. All of that is a constant. That is the mass of the thing that everything is going around. So for everything that's going around the sun, the ratio, all of the planets have a ratio of their period around the sun to their radius of the sun that comes to that. It's 4 pi squared divided by g, which is a constant, and divided by the mass of the sun, right? Everything that's going around the Earth, like the moon and satellites and all that sort of stuff, their ratio of the period squared to the radius outside Earth is cubed. That should be up there, by the way, not down there. I've just realized that. Radius cubed is the same. It's a different number to the sun's number, right? Because it's got the mass of the Earth there. But that's, excuse me, but that's sort of the beauty of this. If you know this ratio for one thing that orbits the sun, then you know that ratio for everything that orbits the sun. It's a really good shortcut. But it only applies when you've got a period and a radius in the same question. Otherwise, you're not going to use it. Okay, question 3. Phobos is one of the moons of Mars. It orbits at an approximate distance of that far from Mars. There's the mass of Mars. There's the mass of Phobos. What's the force between the two of them? Okay, this is the force between any two objects. It doesn't matter whether they're planets and moons or whether it's a pen and an eraser. Okay, mass of Mars, mass of Phobos, radius g. You've been given on the formula sheet. Figure it out. Comes to that. Easy. That should be a very easy 2 marks. Right. What's the orbital speed of Phobos? Show you working. There are 2 ways to do this. One of them's really long and involves Kepler's third law followed by velocity equals distance over time, which is 2 pi r in this case because it's a circle. Don't do it, for God's sake. Shortcut, right? F equals mv squared on r. The force, that force that you just found happens to be the force that's required for that mass to go around that radius at that velocity. So figure out the velocity. Easy. It's actually a lot easier than it looks. A lot of people are going to do that the hard way. It's going to take them 10 minutes. This is 2 minutes. All right, brings us to question 4. And this one strikes fear into the hearts of many. I understand this. So let's have a look at this. 200-gram ball is attached to the end of a string and swung in a horizontal circle like this, as shown in figure 3, which I've reproduced over here. The string forms a constant angle theta with the vertical. The ball's constant horizontal speed is 1.96 meters per second, and the radius is ½ meter. All right, calculate the tension in the string, show you're working. Ouch. Right, 3 marks. Okay, here's what you can do. This is the deal. Whoops, sorry. Let's get my working here. Vertically, there are two forces on this, and they're in balance because the ball isn't going up and it isn't going down. It's in a horizontal circle. So it's not accelerating vertically at all. So you know that the two vertical forces on it are equal to each other. They're equal and opposite. And that's mg, that's the mass trying to pull it towards Earth, and that's t cos theta, right? Because that's t, and that'll be t cos theta, and that'll be t sine theta. Okay. So they equal each other. So you've got a formula here, t cos theta equals mg, right? And you can figure out what t cos theta equals, right? Horizontally, the only thing is the horizontal component of the tension, which will be tension sine theta, right? Excuse me, sorry. So, because you know that it's traveling in a circular path, horizontal circle, you know that t sine theta, that force, is equal to mv squared on r, right? The old circular motion formula. If that force is causing a circular motion, it's mv squared on r. So you can solve that to find out how much force it is. You don't know t and you don't know theta, but you know what? You know those three, so you can figure out what that is. And having done that, you just use Pythagoras' theorem. Right? You've just found out what that is. You've just found out what that is over here, right? And just use Pythagoras, right? R squared equals A squared plus B squared, etc. Right? 2.49 newtons. It's a lot of mucking around. It's a long process, but each process is pretty straightforward. But it begins here. A lot of people never even start a question like this because they just don't realize that that's how to start it. All right. All right, question 5, and this is one, again, this is one that 1,000 people are going to get wrong. In fact, they're going to get 0. This is a particularly difficult question for people to answer because you have to explain stuff without using any maths. And that strikes fear into your hearts, I know that, and a great many others. So if you can get good at this sort of stuff, you're going to leapfrog a lot of people. So let me show you this. Right. Figure 4 shows a 1 kilogram ball attached to the end of the string in 2 positions, right? Firstly, it's just hanging there. Secondly, it's swinging like a pendulum, all right? Right, it's the lowest point on its swing. That pendulum, that pathway is going to be circular, right? That's the key. It says using physics principles, so you have to use physics principles. Compare the tensions in the string. When the ball is in position X and the ball is in position Y, that's what you're doing. You are comparing, right? Your answer must clearly be a comparison. So for the love of God, do this, right? You can divide that. You don't, just because they've put lines there, that doesn't mean you have to write stuff. Doesn't mean you have to make it a paragraph. It doesn't have to look like prose. You can cross all that out and do a diagram down here if you want. How you answer it is your business, right? If I were you, in a comparison, any comparison, you go, there's one option, there's the other option, that's the comparison. This is exactly how to get this done. Right? So, at X, you had this situation before, right? That will equal that because the thing isn't going down and it isn't going up, so mg equals tension in the string. Easy. That's all it is. The overall force on the ball is 0. There's nothing else to say. Okay? At Y, the tension on the string is going to be bigger because not only does the string have to hold it up, right? Over here, the only thing the string had to do was hold it up. So it just has to match mg. So mg has to be tension. If that's 10, that's 10. Now it's got to do 2 things. It's holding it up, but it's also swinging it in a circle. It's also providing that F equals mv squared on r. That force has to happen as well. So this string needs to be doing a bit more work here, right? If you can imagine making this a really fast swing, eventually the faster you swing it, the more likely it is for the string to break because it will need more and more and more force to hold it in the circular path. It's doing 2 jobs now. Right? So the tension here is equal to mg, just like that one is, right, plus mv squared on r because it's doing 2 jobs. It's holding it up against gravity and it's pulling it around in a circle. And that's all you have to say. But make it a comparison. This is option X. This is option Y. Make it as clear as day, right? I've got that. This is exactly what I would say in my answer. Right? So you can read that. You can pause this and read that at your leisure. But absolutely do this. Put a line down the bottom and go at X, at Y. That's a comparison. Okay, question 6 is another one that a lot of people don't like, projectile motion. It's got a champagne bottle. It's going to blow its cork. The cork weighs 10 grams. It starts 1.2 meters above the ground, and it's going to be popped out of the bottle, and it's going to reach its highest point 0.8 seconds later, and it's then going to hit the floor later on. Right? Part A, what is the maximum height? Right? After 0.8 seconds, how much higher has it gotten? Now, when I started to write the answer to this, this is what I did. I started setting things out like this. Right? I went over here, I went vertical figures, horizontal figures. I didn't know at the time that I didn't need any horizontal figures, but I just did that. And that's what you should do first. Every time there's a projectile motion question, just get all the vertical figures and the horizontal figures. And because I needed the figures just for a part of the flight, because the question says, what is the maximum height above the floor that the cork reaches? Right? So we're not going to the floor. We're not doing this. Right? We're not going like that. Right? We are only going from there to there, right? To the highest point. So that's the trip that these figures are for. Right? The final velocity of that trip vertically is 0, because at that instant the thing is traveling horizontally. It's not traveling vertically at all. So that's why I know V is 0. Right? It's accelerating at negative 9.8. Positive is up, negative is down. And the time of that flight is 0.8 seconds because they gave that to me. So that's what I've got to play with. Pick the right formula. Right? There is a bunch of these, all the equations of linear motion, V equals U plus AT, all of those. There are 4 or 5 of them. Pick the right one. This is the right one. Right? You don't have U, so you've got to get something that doesn't have U. Right? And basically find the answer, and you get 3.14 meters. Now, a lot of people are going to do all of that right and leave it at that, but that's not the answer, because this thing started 1.2 meters above the ground. And the question says, what's the height above the ground, above the floor that the cork reaches? So you have to add on the height above the floor at the beginning, right? And it gets to a height of 4.34 meters. All right, so that's part A. Part B, and I'll fix this in a minute. Part B, determine the gain in kinetic energy of the cork from its initial position in the bottle to when it strikes the floor. Show you working. Okay. This is a conservation of energy question. You can do this a much longer way using some of this stuff, and one of these formulas. However, again, I'm all about doing it the easy way, the fast way. This is the fast way. Before it shoots out of the cork, all of the energy that it has is gravitational potential energy. So that's the total energy. And when it lands, as it hits the ground, all of the energy it has is kinetic, right? And so that'll be the total energy as well. And of course, conservation of energy tells you that the total amount of energy that the thing has is going to be the same from start to finish. It just changes from one form into another. So you can just figure this out, right? You can't figure out kinetic energy very easily because the V down there is going to take you half an hour to figure out. You can work it out, but geez, don't bother, right? Because you don't have to. Right? Because you've got M, you've got G, and you've got H, so you can find that and you know it equals that. All right, so that'll be the change of energy, 0.12 joules. Right, question 7. You might have already seen I've written ambiguous question here, because it is. So let me show you how it's ambiguous. They're assuming that you're going to assume something that you might not assume. That's why it's an ambiguous question. So here's the deal. If we're looking at that from the side, then that's the top and that's the bottom. If we're not looking at that from the side, that's not the top and that's not the bottom, right? You absolutely need to understand that that really is above that and that that way is down, because otherwise this question is irrelevant. It doesn't work, right? But they didn't tell you that. They didn't say viewed from the side, or they didn't say top sphere and bottom sphere, etc. They mentioned it later on. But They've just assumed that you realize that for example, you're not looking down on this from above or up from below, that's just looking straight ahead, and that's directly above that. The VCE rarely makes mistakes like that. I used to be on a team that wrote sort of the New South Wales version of VCE questions for the Catholic education system. So I sort of see these things very easily. The VCE are really good at avoiding things like that. But this is a classic case of a bit of ambiguity that wasn't really mentioned. And unfortunately, it tends to penalize the best students, because the really smart students who are looking for every little detail will figure that out. And they'll go, oh my God, maybe we're looking at that from above, and they will make this question more complicated than it is. Right? Unfortunately, this was left open to that. It should have said viewed from the side, right? Or they should have labeled that top, bottom, or they should have said this is pointing down, something like that. The VCE won't make that mistake. They're professional. They're very good. Okay, having had that rant about this, let's answer it. Calculate the magnitude of the electric field at the sphere's position. You need to know the formula. There it is. Right? V on D. They told you the voltage. They told you the distance. Put it in meters. Right? Don't make a rookie error. And that's the answer. Okay. On figure 6, label the positive plate. Label it very clearly. Keep it simple. Just do this. Big fat arrow. Positive plate. There you go. No one's going to give you wrong for that. Okay. You know that the top plate is positive because this is a negatively charged sphere, and if it's going to be held up, it needs to be being forced up by something, and it's being forced up by the attraction of a positive plate. Right, that makes sense. So that's part B. Make it really clear. Calculate the mass of the sphere. Show you're working. Because it's suspended there, it remains stationary upon being placed in the position. It doesn't fall, it doesn't rise. That means, of course, the weight pulling it down is equal in magnitude to the electrical force pulling it up. And they're the two formulas, mg, qe. They must be equal. Solve it for m. Pretty straightforward. Question 8 is another one where you have to be very good at explaining something. This is a real test. 3 marks. As part of a project, a pair of physics students built a DC motor. All right, so they've got a battery, they have a DC battery, and away it goes, right? You know the deal. Split ring commutator, doing the right thing, AC on the inside. Good. The students switch the battery on and the coil rotates freely, so it should. One of the students states that the sum of the forces acting on the coil is 0, and that is true. Explain why the coil rotates if there's a net force of 0 acting on it. Okay, so if you do your right hand rule, oops, sorry, hang on. Let me just fix that. Now you notice, by the way, that they didn't tell you which one was positive and which one was negative, so it doesn't really matter. So you can invent it yourself. So I'm just going to say that side's positive and that side's negative. All right. So in that case, right hand ruling it for positive charges. Positive charges will be going in, and they'll be going from E to F. Right, so if I point my thumb going from E to F and my fingers going from north to south, then I'm pushing E to F down with my palms, if I sort of do that. Right. On the other side, I'd have to go like that, and my palm would be pushing up. So the forces go like this. There is a downward force on EF, and there will be an upward force, equal and opposite, on GH. So you need to make the point that this is why the net force of 0 is acting on it, right? Because they're two forces that are equal in magnitude and opposite in direction. So yeah, if you add up all the forces on that thing, it comes to nothing. So why the hell is it moving? It's because of torque, right? Torque is the turning effect of a force. And that force there has the effect, right? It is trying to pull down, but the effect of it is to make EF go anti-clockwise. And the effect of the opposite force on the opposite side is to make GH go anti-clockwise. So while the forces disagree with each other, one of them is down, one of them is up, what they do to the loop agrees. They're both pushing the loop in an anti-clockwise turning direction. Right? So the two forces cancel each other out, but the two torques don't. They agree with each other. They add up to a non-zero number, and that's why it still spins. So again, if you want to read, like I've put a few figures on it here, right? But they're the essential parts of a good answer to this question, all right? You need to make the point that the forces, yep, they do add up to zero. However, the effect of those forces in turning something is not opposite, right? They're both going anti-clockwise, and so they agree with each other, they help each other, and the torque is not zero. Question 9. All right. A single beam of positive charges goes down like this, and when it hits here, it goes into a vacuum with a magnetic field. So there's nothing there to stop it. There's nothing they're bashing into. It's a vacuum, but they are in a magnetic field and they start turning. And the one beam of stuff splits into two different beams of stuff, but they both end up turning left. All right, and they're detected by this detector. That's what that is essentially saying. State two factors that could have resulted in path B having a greater radius than path A. All right. So they were going at the same speed, right? The single beam of positive charges travels, right? The beam separates into 2 points. Hang on, said the same speed. Hang on, where did I get that? Hang on a minute. Yeah, the charges enter the magnetic field with the same speed. Sorry, I knew it was there somewhere. Okay, so here are the things. The force that the magnetic field is pulling on these things with is F equals QVB. Right. Because they are pulled into circular paths, we get back to this again, F equals mv squared on r. That force is having this effect. Right. So they are moving in a circle, and this is what's causing it to happen. Right? Velocity is not a factor. They're going in at the same speed. So anything else that you could change in either of these could be a factor. It's likely that one thing is lighter than the other. Maybe there are protons and, not protons and electrons, that's a bad expression. Protons and alpha particles, which weigh 4 times as much as a proton. They're both positive, but the heavier one will do the bigger circle because it's harder for the same force to pull it around in a circle. All right, it's a bit like turning a truck versus turning a motorcycle. They're more nimble, right? Ruck versus rover. Or Q could change, right? Maybe some of them had a, had a higher charge, and if there was more charge, there'd be more force on you, and so you would be whipped around faster with a bigger force. All right. So this is the way to do it. Okay. Analyze the formulas. Easiest way to go. And the other thing about a question like this, it says state, so you don't have to explain it. So don't waste your time explaining it, right? You should state them. You should say charge or mass of the particles, charge on the particles. That 6 words is 2 marks. Don't waste your time writing any more than that. That's the answer. State. Right? State. Don't explain it. Don't waffle on. Don't write down here. Okay. State the direction of the external magnetic field. Okay. There's something else I need to remind you of here. Firstly, let's answer the question. Okay. We're doing the right-hand rule thing again. They were positive charges. I'm just going to upend my page because I can't upend my wrist. All right. So, right hand, thumb is pointing where they're going. Fingers, I don't know yet, but I know that my palm has to end up going that way, right? My palm has to be pushing these things sideways to your, whatever it is. I've got things upside down now. I can't even speak. Right, so my palm has to end up going that way. My thumb has to start going this way, and I've noticed that my fingers are pointing into the page. So that's the answer to the question. Now, it is important that you don't say down. Even though that direction is down, right? My fingers are pointing into the page, but they're also pointing towards the floor at the moment, of course, and that's down. I get it. But you need to say into the page because officially, according to this diagram, that direction is up, even though the page is horizontally on a table, right? And that direction is down, even though that's actually not up and that's not down, right? Up is towards the top of the page, down is towards the bottom of the page. That direction, which is currently down, it's the way things fall, right, is called into the page. Don't get it wrong. So state the direction of the magnetic field into the page. And again, say it and stop. 1 mark, no time. All right. Question 10. Now this is the last question I'm going to do for this file. The last file that we're going to have is going to do questions 11 to 17 and that'll be it. So let's get this. Let's have a look at this first. Here's the question. I've redrawn it over here, but let's have a look at it. Square coil, side length 10 centimeters, consists of 10 turns. The coil rotates like this. Okay, so it's doing that. At a rate of 1 hertz. Now that means 1 complete turn in 1 second, right? That means not that, but all of that, right? From there to there in 1 second, right? Be aware, it's a full turn. It's not just a flipping over. All right. Magnetic field strength they gave you there. All right. Calculate the magnitude of the flux through the coil. This is just know the formula. Here we are. So there's the formula. BA, they gave you B. They gave you the way to figure out A. Convert centimeters to meters. Don't make that rookie error. Get the answer. It's 1 by 10 to the minus 3 Webers. Okay. Remember that it's in Webers. They even gave it to you in this one. B, calculate the average EMF developed in the coil during 1/4 of a full rotation. Now they picked 1/4 of a full rotation because that goes from maximum flux when there are the maximum number of magnetic field lines pointing through to no flux. Okay, so the delta flux is the whole thing, right? We just calculated what the flux was. So it's going to go from 1 by 10 to the minus 3 to nothing, right, in that time. And it's going to take 1/4 of a second because it's 1/4 of a rotation. All right, so let's have a look at this. This is the formula for EMF. It's got a negative there, right? Keep it in. The N is 10. They told you the thing had 10 turns. Right? A lot of people are going to miss that. A lot of people don't read the stem. They just look at the numbers. And if they miss that one, all right, so the N is 10. Delta flux is going to go minus, right, because it starts off with all of the flux and it's going to end up with none of it, all right? So it's a minus, and that makes this positive. That's why the minus is there, actually, okay? Divided by 1/4 of a second, that's the answer. Okay. Part C. Explain how that answer, your answer to part B, would change if the coil rotated 4 times faster. Right? No calculations are required. You cannot do calculations. Right? That basically, that's not saying, you know, you can put calculations in if you want. Right? That is ordering you to answer this question without calculations. Right? You have to do it without calculations. You can put calculations in there, but if that doesn't, but if the question, but if the part of your answer that isn't calculations doesn't answer the question, you won't get full marks. So you've got to answer this without a single calculation. Right. So here's how you go. This is an answer with no calculations, right? 4 times the rotation rate leads to 4 times the rate of change of flux. Okay. You can quote the formula again if you need to. Right? And you're just therefore saying, therefore, EMF would be 4 times the original value. I didn't calculate anything there. I didn't find out what 4 times the original value of anything was. I just said that everything would be times 4. That's all you have to do. All right? So don't waste your time with calculations. Part D. Draw an arrow on figure 9 to show the direction of the induced current in the coil. Okay. I'm going to show you a different way to answer it from the way that the NEAP people have done it in their answers, in their suggested solutions. They've done it in terms of flux and Lenz's law. I think that's a complicated way to think about it. I think it's easier just to sort of right-hand rule this thing. All right, so Side AB, and again, you can do this in the answer. You can change the diagram. You can say C diagram, right, side AB, and put an A and put a B there. There's nothing stopping you from doing that, right? You can amend anything. Okay, so that is moving downwards as seen in the diagram, right? So as this thing is spinning, that top is going down and the bottom is going up. Have to make that point. The right-hand rule states that a positive charge that is stuck in that wire there, right, moving down, remember down, not into the page, down, right, in a magnetic field directed out of the page, will experience a force to the left, in other words, from B to A. So if you put your fingers out of the page and you have the thumb moving down, I can't do it under the camera, right, you'll end up getting your palm going that way from B to A. Right? And so that will induce a current anti-clockwise because everything along here is going to go that way. You could say, you know, for CD, it would be going the other way, but I think you've made the point by the time you've said that much. You just have to say then that'll make a current going anti-clockwise. That's fine. Right. There you go. And don't forget to do the other part of the answering of the question. Read the question. It does say draw an arrow on figure 9. So if you've answered it beautifully here, if you've drawn your own diagram here, and that's not figure 9, right? That's your diagram, and you do it perfectly here, but you didn't actually go and flip the page over and do it on figure 9, they can't give you full marks, right? Keep all this in mind in the VCE exams, all of them. You are a slave to the question. You need to do exactly what it says. So if they say draw an arrow on figure 9, do it. Right, that, my friends, is it for this file. The third and final file will have questions 11 to 17. Thank you.